anyways, thank you for that generous introduction. Yeah, so it's actually a very common question that people come to us. One of the main reasons that people come to our imaging facility, overwhelmingly, they're coming to us for confocal. They come to us and they say, I want to learn how to do confocal. And they don't really know what kind or what the different kinds of confocals are, or even they probably don't even know whether they really need confocal or not. It's just someone told them, you want better images? Go to the facility and get some confocal images. So what I'm hoping to tell you about today is a bit of a comparison of different confocals. And it's most heavily weighted on two different kinds of confocals, the classic laser scanning confocal and the spinning disk confocal. But I'll throw in a third instrument as well. So first of all, is this coming through okay? Do you want to turn the lights down a bit more, or is it okay? It's okay for you guys? All right. So there's already some misconception about what a confocal of any sort is good for. And some people have different ideas. They think maybe it's for better resolution, maybe it's for better sensitivity. But the real purpose of a confocal is to do something very special, which is called optical sectioning. So it's sort of related to the depth resolution, but it's more appropriate to call it optical sectioning. So you see on the left a wide field microscope, and it's not that there's not a lot of signal there. There's plenty of signal. There's lots of fluorescence coming off that sample, but there's always a mixture of the in-focus sharp image and the out-of-focus blur. So those are all mixed together. So even if you focus, so I'm just focusing through this kidney section, and the confocal can block out the out-of-focus stuff and just give you a sharp image of the in-focus stuff. That's in a nutshell what confocal is for. So if people come to me and say, I can't see my sample on a regular fluorescence microscope, can you help me to do confocal so that I can see it? Because then I say, well, why can't you see it? Is it because there's too much blur? No, it's because there's not enough signal. Well, that's not actually an application of confocal. Confocals have this important property of blocking the out-of-focus light. Okay, then these are the three types of confocals that I'm going to talk about, because they all have their advantages and disadvantages, and I'll spend most of my time talking about the first two, the laser scanning and the spinning disk. Surprisingly, how well a microscope performs depends on what you're looking at. Like, a lot of people don't really think of it that way. But if you're looking at a very thin sample, then you basically don't even need confocal. But if you are using a confocal, this sample can show you, because it's so nice and thin, you can really tell how well the system's performing in terms of resolution and things like that. So I like that as a nice test sample, but it's almost too thin to bother with confocal. The intermediate one there is about 10 to 15 microns thick, and you definitely start to see an advantage using confocal over wide field. And then there's a thicker sample there that's a little more challenging. So I'm going to compare these. So I tried to use these three samples on the various microscopes to compare how well they're performing. Okay, so here's how the confocal works. This is the principle of confocal. And this explanation is most applicable to the first one, the laser scanning confocal. So what you do is you take a laser beam and you focus it down into the specimen. And you focus it down to a tiny, tiny spot. This is going to become 1 pixel in your image. If you zoom in on that, you can't see it maybe too well on the screen, but could you see that I've generated fluorescence there in the focal point? I worked really hard on that, so I'd like you to be able to see it. So you generate fluorescence in that whole cone of illumination. And even though it's most concentrated at the focus, you've generated a lot of fluorescence near the surface especially, and down below as well. So then the whole trick to confocal is that you don't allow the fluorescence from the surface, for example, to come to your detector. So if you look on the right-hand side, I've broken out the emission path just for clarity. So any fluorescence that does come from the focus is collimated by your objective lens again. It forms a nice collimated beam. And then you have a second lens that focuses your beam through a pinhole onto the detector. So that pinhole is sort of the whole key to the confocal. The smaller you make the pinhole, the more confocal you get. In other words, the narrower a slice of the sample you end up imaging. So any light from, any light that happened to come from the surface, for example, because it didn't come from the focus of the lens, it ends up getting blocked by the pinhole. It's not imaged through the pinhole. So with that simple idea, so that actually just gives you 1 pixel in the image. And then you have to scan your laser beam back and forth across the sample in a raster pattern, and that gives you 1 image plane. And then you just change the focus and do it again, and that's how you get a whole 3-dimensional volume. OK, so here's how a laser scanning confocal performs. This is that very, very thin sample. And you basically don't need confocal for this. On the left is just a wide field image. And you can see that if you choose the right focal plane, it's a beautiful, sharp image. On the right, you see this special property, though, where when you go out of focus, instead of seeing blur, it just becomes completely black. So that's what a laser scanning confocal does. So you can imagine now if you had a much thicker sample that's made up of many focal planes, how this is going to become important. So if you look at this, this intermediate thickness sample, I already showed you this at the beginning. It's really doing a great job of just giving you 1 focal plane at a time. And it has no problem at all with this sample that's almost 50 microns thick. Even right down to the very bottom, you can clearly make out the individual nuclei. So a laser scanning confocal can quite easily go 100 microns deep. And after that, it depends a lot on the sample, whether you can go deeper. So the laser scanning confocal, I would call it the standard confocal. This is the classic confocal. This works for many kinds of samples. And let's take a look at 2 properties of the confocal. Let's think about its resolution for a minute and its field of view, because this confocal really excels in both of these areas. So resolution is, the Rayleigh criterion is a simple formula for resolution that depends on the wavelength of light and on the numerical aperture of the lens. Okay, maybe you've seen, who's seen this before? Some of you seen this before? So it actually doesn't depend on the magnification of the lens. You should note that. It depends on the NA of the lens. And a lot of people haven't even heard of NA. This is the focusing angle of the lens. So you can have 2 40 times lenses, one with a very low NA and one with a very high NA. And it's the NA that matters for resolution. So if you plug in a couple numbers like green light for GFP around 500 nanometers or 0.5 microns, and if you use our highest NA lenses, which would be an oil lens, like a 60 times oil lens, plug in those numbers and you realize that you should be able to resolve structures around 200 nanometers. So that's pretty good. Now, you'll only resolve those structures if you've used enough pixels. Okay, so this becomes really important. So here's a photo of my dog Fresco, who passed away a couple summers ago, by the way. But I still like to show this. Obviously, if I use, I think that's 32 by 32 pixels, it's not enough to capture the full resolution of what the lens and the optics and everything did for me. And if I use more and more pixels, I start to get closer and closer to really reproducing everything that lens was able to give me. So in the confocal, there's something called the Nyquist Theorem, which says that you need at least twice as many pixels as your smallest resolution element. So if your best resolution is 200 nanometers, your pixels have to be about 100 nanometers big. So the great thing about the laser scanning confocal is that because you're imaging pixel by pixel, you can actually decide where you take those pixels from. So you could zoom in on one single nucleus, and then if you calculate out how many, the numerical aperture of your lens and whatever, you can decide, oh, well, I only need to take 512 by 256 pixels to capture everything that that lens has to offer. Okay, so this is only about 15 microns by 30 microns in size, this image. Or if I want, I can zoom out, and mind you, this is a different lens. This is a 20 times lens. But I can zoom out and get a huge field of view, but still capture it at full resolution if I just use enough pixels. So I have the flexibility in a laser scanning scope of saying, well, now I want to image with 2,000 by 2,000 pixels. And this would let you then zoom in and still see the nuclei individually and quantify accurately how many nuclei are labeled, but for a relatively large structure. Yes?
James, this is for, you're talking 2 dimensions here. When you talk about optical sectioning, you have that 3rd dimension of depth. So
yeah.
How do you know if you have a 100 micron section, how do you know what the optimal thickness of your optical section should be to maintain the resolution?
Well, there's a most of the confocals have a let you change the pinhole size, and they have a button called the optimum button. So it's actually a very complicated formula to try to work out for yourself what the optimal size for the pinhole should be. But it should match the point spread function, if you know what that is, the point spread function of your objective lens. And you should set it to just a little bit bigger than 1 area unit. But the nice thing about a laser scanning confocal is that you can play with the pinhole. So you can set it to the default, and if you're not getting enough light, you can open it a little bit. Or if you really need to resolve the finest, get the best resolution out, and you have enough light, you can close it a little bit. So you have that flexibility. Okay, so this is why I would say that the laser scanning confocal is your most general purpose confocal, because you can use it in different ways and always get the field of view that you want and the resolution that you want, the sampling, the number of pixels you want. So it really has the best optical sectioning performance for thick samples. You can really maximize your field of view while maintaining your resolution. It's flexible. If you have a sample that's very dim, you could open the pinhole up a little bit, things like that. The main disadvantage is that it's a little bit slow. That's one of the main disadvantages, because you're imaging pixel by pixel. If you want to do 2048 by 2048 by, say, 10 slices in the depth direction, that might take you several minutes to acquire. So it can be a little bit slow. And for live cell imaging, you can definitely have a problem with photo bleaching. So the confocal works by throwing away light. You generate light in this whole cone of illumination, and you throw light away. And so the detectors that we use in the confocals are not the most sensitive out there. So it's, but they're fast, and you need them to be fast. So it's not the answer for all of your imaging, but I would say it's the most general purpose confocal. Okay, so next we'll move on to the spinning disk. And since one of the big drawbacks of the laser scanning confocal is that it's somewhat slow, and this is because you're imaging just 1 pixel at a time, why not image about 1,000 little beams at a time? Have 1,000 little beams going onto the sample at a time, and 1,000 little pinholes. Then you should be able to speed everything up by a factor of 1,000 in principle. So that's the idea of this spinning disk confocal. You use a clever arrangement of little holes. As the disk rotates around, you end up, the next row of pinholes fills in where the previous row missed. So as you rotate the disk around, you end up covering the whole surface of the sample. But at any given time, you have about 1,000 little beams going. So the company Yokogawa thought the Nipple Off Disk is quite old. Originally, they wanted to use this for television instead of the cathode ray tube. That's what it was designed for. So this is a very old idea. But Yokogawa said, well, you waste a lot of laser light with the lasers just hitting that big disk that that has all the holes in it, why not have another disk that's full of little lenses to collect the light and purposely send it through each of the little holes? So this is how most of the spinning disks look like now, with two disks that rotate together, and in between them you have a beam splitter that sends the light to a camera. So now instead of a single point detector, you have a CCD camera that collects all the points in parallel. So you can see how this might speed things up. In fact, if you wanted to, you could do up to 360 images a second with this kind of thing. In practice, that never happens because you can't set such a short exposure time. You don't have enough light. Okay, there's another version that Olympus has made, but it's maybe not that interesting. So here's where the spinning disk confocals really shine. So they were always meant to be a solution for faster imaging, right? So they really shine when you're trying to do faster live cell imaging. So on the left you have microtubules moving around. If you look closely, some of them are growing and shrinking. Can you see some of them growing and shrinking? It's hard for me to see from here. If you don't have confocal, then the free GFP in the cytoplasm obscures the microtubules and you have trouble seeing them. So you really do need confocal to see the microtubules very well. But you need a certain speed, and on a laser scanning confocal, even if you were to take just a small area, so that you can scan a small area pretty quickly on a laser scanning confocal, but you will do a lot more photo bleaching. So the laser scanning confocal is gentler on the cells. Part of the reason is that instead of a detector that has to detect each pixel one at a time, you have this very sensitive camera, which is a lot more sensitive than those point detectors are. Here's a case where you see the free GFP. This is N-cadherin GFP, and at the point of contact of the cells, it's very rapidly recruited there. And again, this is something. These movies in live cells, this is really what the spinning disk confocal was designed for. When you get to thicker samples, though, it can still work. So you can see how with this 10 micron or so kidney section, 10 or 15 micron thick kidney section, it still is more or less confocal compared to that wide field image there. So it is able to do optical sectioning. But when you get even thicker, you'll see that there's a lot of haze in this image still. So it's not doing as good a job of blocking out the out of focus for this sample that's, this is only going about 40 microns deep, and already it's having trouble. So what happens is, yeah, and here's a very thin sample. For a thin sample, you do get this confocal effect where as you go out of focus, it's black. It's not blurry like the wide field. So it is really doing confocal, but you do have a decrease in optical sectioning performance when you get to thicker samples. And this is the key, that as the sample gets thicker, now instead of the pinholes blocking the light, you have a lot of scattering happening. So what happens is the light goes into the wrong pinhole rather than being blocked from getting to the detector altogether. So the thicker the sample, the more of this, what we call it crosstalk between the pinholes, the more crosstalk happens. And you become less and less confocal as the sample gets thicker. So if people are doing animal imaging, you might be tempted to say, oh, a spinning disk is great because it's really fast. Okay, yes, it's fast, but it's exactly the wrong approach when you have a very thick sample, because it's not very confocal for thicker samples. Okay, so I already mentioned that spinning disks are based on cameras rather than point detectors, and these cameras are very, very sensitive, and this is part of the reason that they work so well for live cell imaging. So these cameras, not only are they very sensitive, but also part of the reason they're so sensitive is they have very big pixels. So most CCD cameras that we use in the microscopes are at least 1.4 megapixels, which is still, I don't know, a quarter of what you guys all have on your phones, right? Which are usually like 5 megapixels at least or something. So in microscopy, we're happy with 1.4 megapixel cameras. But for this application, we actually use cameras typically that have a quarter of a megapixel. These are our most expensive cameras. These things are $40,000. So but their specialty is not resolution. Their specialty is sensitivity. One of the reasons they're so sensitive is they haven't broken your light up into such tiny pixels. They've left the pixels nice and big. So they're these huge 16 micron diameter pixels instead of 6 micron diameter pixels. So that's part of the reason they're so sensitive. But with so few pixels, you really compromise on the sampling. So remember we said that, that you need enough pixels in order to capture all the resolution that the lens is giving you. And you can't do that with these cameras. You either compromise on your sampling, so you really degrade your resolution, or you have to zoom in on a very small field of view. And you don't actually get to choose sample by sample. It's set for you by the manufacturer when they install your scope. And so I'll show you what ours looks like for both of those parameters, the sampling and the field of view. So first of all, the sampling or the resolution. So remember this slide where I said that you need, if you have this 1.4 NA, like our highest resolution lenses, you can resolve structures at about 200 nanometers, but you need to use 100 nanometer pixels. And on our spinning disk, if you use a 60x objective, you're oversampling. The pixels are too big. They're about 270 nanometers. It's only when you go to the 100x objective that the sampling is actually matched to the lens properly. Okay, but now you get a very tiny field of view. That's the problem. So, they generally have lower resolution just because you introduce a lot of pixelation. So this image looks good when you zoom out like this, but when you look carefully, can you see that the top one there is pixelated? Can you see it from there? What's interesting is when they demo these spinning disks, because our eyes are so distracted by pixelation, they actually do post-processing called smooth zoom, or use whatever euphemism you like, interpolation and blurring, that just guesses and ends up turning pixelation into blur, which is less distracting to our eyes. And so whether you use Velocity or Zen or like any of these software packages, they tend to have by default this nice interpolation method, so you don't really notice the pixelation. But it's there, and it's degrading your resolution. If you even compare this to just a capture off of a wide field camera, the wide field camera with more megapixels looks better. So the spinning disk is not a resolution specialist, to say it nicely. Okay? And so our microscope, it's not so bad for resolution. You can see the pixelation, but it's not so bad. What Quorum did when they set up our WaveFX is they said, well, we don't want to degrade the resolution too much, so we're going to really optimize it for 100x. We realize most people will use it with the 60x objective to get a bigger field of view, but we're willing to compromise a bit on that. But now look at what we have to compromise in with the field of view. So this is the field of view. I think this is a 20x objective on our spinning disk confocal. If I move over to our laser scanning confocal and use the exact same objective, I can get this huge field of view, right? And I can choose how many pixels I use, so I can use optimal sampling, get a huge field of view, and see this entire thing. It's exactly the same area, same sample. And so for tissue imaging, where you tend to want to see large structures, the spinning disk is exactly the wrong tool. It's exactly, and the sad thing for me is to see people who bought they had funding for one confocal, so they bought a spinning disk. And then they, of course, use it for everything. And they bought a spinning disk because they thought they were going to do a lot of live cell imaging. But also they were probably unaware of these things. And they end up doing a lot of fixed sample imaging. And I've seen people who are using a spinning disk to image tissues where they actually wanted to image kind of large structures, which is exactly the specialty of a laser scanning confocal. And instead, they're zooming out, like using a low mag objective, so that it's almost not even confocal, and or they're doing tiling and stitching, like trying to stitch together a whole bunch of fields of view. And all they have to do is move to a laser scanning confocal. So I don't have a great slide to show this, but this is a 10x picture of that same tissue. And what I wanted to show is that at 10 times, a spinning disk is indistinguishable from a wide field microscope. There's no optical sectioning left at all at 10x. So not only do you have a problem with lateral resolution because of the pixelation, and you have a problem with field of view, but the third thing is that spinning disks, the pinhole size in that disk is matched for 100x. And it works okay with 60x. But when you get down to 20x, it's almost not confocal. And when you get down to 10x, it's absolutely indistinguishable from a wide field microscope. So you would always get much nicer images from a good wide field scope than you would from a spinning disk at 10x. And yet, because the field of view is so small, people find themselves going down in mag. So you go down to 20x or 10x, and it's not even confocal at 10x. It's exactly the wrong approach. Is this going to advance for me? But I'll end off on a positive note for the spinning disk section. Here's an image that my colleague Feng, who works with me at the AOMF, he captured this just the other day. And this is, I think he said it was EB1, labeling, does it label one of the ends of microtubules? I need a biologist here. This is where being a physicist becomes a disadvantage. So I think the idea was to measure microtubule dynamics, and I think that labels the leading edge of these things. And so you can actually quantify the dynamics of these things as they grow. And I have to admit, this would be difficult to do on a laser scanning confocal because of how many images you need, how fast you need them. This was not super fast. This was a couple images a second. So that's fast enough that you would like to have the EMCCD capturing many pixels at the same time. I'm not going to zoom in and show you the pixelation because it's definitely plenty good enough to measure the dynamics that I'm looking for. So it's partly microscopy is about pretty pictures, but at the end of the day, it's about getting data, right? And you can do tracking of these. The quality of the data is good enough that you can do tracking. And because that EMCCD is about 2 to 3 times more sensitive than the detectors we use in laser scanning confocals, you can reduce your exposure by 2 to 3 times. And that really helps to get this kind of data. So for live cell imaging, if you're willing to go with a small field of view, this can be a great tool. But it's not your general purpose confocal. OK, so the advantage is for fast live cell confocal imaging, less phototoxicity and photobleaching, but the disadvantages are very real, and it basically rules it out in my mind for tissue imaging or really for any fixed cell stuff, because it's not very confocal for thicker samples. You have lower resolution and or field of view, and it really only works for 60x or 100x. So everyone using spinning disks for 20x, you've just been fooled. Like if you're using a spinning disk for 20x, go find yourself a good wide field scope and compare. In fact, when you look down the binocular, you'll probably see as nice or a nicer image than when you capture it on the camera. So that tells, because the binocular is not confocal, right? It's just wide field. So it's something to consider whether if you're using a spinning disk for 10x or 20x, maybe you should consider finding a wide field scope and comparing. Often, the reason the spinning disk looks so nice is that they have a very good high numerical aperture lenses, like very good quality lenses, a very good light source, very good filter sets, and then the EMCCD is very sensitive. So this is part of the reason you get what you think is a nice image. But if you use a like research facility quality wide field microscope, you may be surprised that it's even better. OK. So I want to tell you about one other confocal. Do I have time? I think so. I've seen quite a bit of people are interested in these these grid-based optical sectioning instruments. So it's sometimes called structured illumination. I don't really like that term because there's a super resolution technique called structured illumination, and it's not the same thing. It's totally different. So I prefer to call it grid-based optical sectioning, but I realize that's a mouthful. If anyone has a better name for this, let me know. But there's a couple of competing brands out there, and I happen to inherit an apotome system, a Zeiss apotome system. And I love this scope because it's a really loaded wide field microscope with a full incubator and multiple light sources and definite focus for like hardware locking in the focus and all this stuff. But it happened to have this little apotome thing on it. So I thought, I've got to take it for a spin, see what it can do. So I had Zeiss come in and realign it, and I'll show you what it can do. So here's the idea. You take a regular wide field microscope and you,
Wait,
yes,
we happen to have one of these in the imaging facility.
there you go.
So pay attention, yeah.
So you take this little device and you plug it into where you would normally put the field diaphragm in a fluorescence microscope. And it's just wide field illumination. I didn't check if I have internet connectivity. I probably can't do this, but you can go to Zeiss's website and see a little animation of this in action. What happens is you project a grid into your sample. So you see the lines here, right? And then if you run this animation, as this rotates, it actually shifts the grid. So it takes 3 pictures with the grid in slightly different places. And it's a very clever little invention by Tony Wilson at Oxford, where if you take those 3 images with the grid in 3 different positions and you subtract them, so you take the grid in position 1 and subtract it from the image you get with the grid in position 2, and then do 1 minus 3, and then do 2 minus 3. Square them, take the square root, and boom, you've done some optical sectioning. It's amazing. It's so simple and it's amazing. And if you add those 3 images together, you just recover a normal wide field image. So immediately you can do optical sectioning. So this is sometimes dubbed the poor man's confocal because I didn't coin that term, but it's pretty inexpensive. It's like about maybe a $50,000 add-in or less to a good fluorescence scope. And away you go doing optical sectioning. So having some real confocals, I wasn't really in the market for this device, but I thought, let's see what it can do. And sure enough, it does optical sectioning. When you're out of focus, it's black. It really blocks out the, like it gets rid of a lot of the blur. And I was pretty impressed with what it could do. I also asked the people in the lab, so in terms of ease of use, you would think, oh, well, there's nothing to do. You just fire this thing up and you get these images. But it's not quite like that. So I asked the people in the lab that we inherited this from. The PI went back to Germany, and a couple of the lab members stayed. And I asked them, so have you been using the apotome? And they said, oh, yeah, we use it. And I said, you mean, so the apotome, you can slide it out and not use it, or you can slide it in and then you're using it. Yeah, I always make sure it's in. And I said, well, in that case, how come when Zeiss came in to go through it with me, they said immediately it's not calibrated for this objective lens? And they said, I don't know. And I said, do you know what happens if it's not calibrated? It only gives you the wide field image. It takes 3 times longer to acquire it, but if it's not calibrated, it won't show you a lousy optically sectioned image. It just shows you a wide field image. You can go back into your data and look at the information along with your images and see whether it actually was in apotome mode or not. And they confirmed, oh yeah, all this time we thought we were doing confocal, and we weren't. We were just doing wide field. So, and it's actually trickier than you may think to keep it aligned. I'll show you in a few minutes in the next couple slides about some of the artifacts you can get if it's not well aligned. And so I don't know whether it's the right approach to scrap your real confocals and trade them in for this device. I think if you have a real confocal, you don't want to give it up too quickly. So here's if I go to this thicker sample. So the intermediate thickness sample, it more or less works. If you go to a thicker sample, you see it doesn't work too well at all. Like it can do some optical sectioning near the surface, but the big problem is you have to be able to see the grid lines. And when the sample gets too thick, you can't see the grid lines anymore, and then it's not going to give you anything. So even with, this was done with a lot of smoothing and long exposure times, and just because the grid lines are too faint in such a thick sample, you can't do it. With a very thin sample where, of course, you don't really need confocal, you can see that it's a confocal-like effect with blocking out, just making it black when it's out of focus. I think, to me, the biggest reason that this isn't so attractive is that you can't always, there's no way to perfectly get rid of the artifacts. I don't know how well you can see it here, but there's horizontal lines from the grid. And I had some other images of the artifacts, but it also, when it reconstructs it, it kind of gives it this mottled effect, because there's a bunch of smoothing, because the noise looks like grid lines, and so they have to strongly smooth out the noise, and so you end up getting even though it's a bright sample, you end up getting this kind of mottled effect. So it's not bad if you don't have a good confocal, but I don't think it's, I don't think you want to trade in. Like if you have a good confocal available, you're going to be more likely to use that for sure. So it's a neat idea, less expensive, although by the time they finished loading up this wide field scope, they had spent almost $200,000, including the apotome. You could have got a confocal for that price too. But it definitely doesn't perform well on thicker sample, and you get some artifacts, and you have to keep realigning it. The vendors will tell you, oh, every time I've seen the vendors show these things off, they say, oh, I'll point out, yeah, but I can see the lines. And they're like, oh, yeah, but if you calibrate it, then you won't see the lines. Well, how come every single time I've looked at this thing, I see the lines? And it's because you can never totally get rid of the lines, I would say. Maybe your experience is different, Judy, but I think you're making do with confocal-like imaging, but it's not the same quality that you're going to get off your real confocals. Would you agree with that, Judy, or you don't want to say?
Our live cell system is optimized for doing long-term. Well, no, I guess for live cell it's not that great because things will move between the three acquisitions.
Yeah. That's exactly, our scope is fully loaded for live cell imaging, and it has this apotome. And we would usually trade in, instead of doing 3 acquisitions, so 3 times the photo bleaching, 3 times the phototoxicity, we prefer to take it out and just let it be a bit blurry.
Well, we've had some, depending on the sample.
It can depend on the application, for sure.
Katarina has used it and has gotten really good images. I always say, let's just try it.
Yep.
You can't always predict it.
Yeah, well, that was exactly a strategy that I used with, okay, let's put several samples on and try them on the different scopes, because it totally, these techniques, how well they work, totally depends on what your sample is.
Yeah.
Okay, so, oh yeah, so here's sort of confocal and apotome side by side. Okay, so I spoke about these 3. I know I spent a lot of time on laser scanning versus spinning disk. And I think, so I'm very lucky that in our facility we have like a bunch of laser scanning confocals, a couple of spinning disks, and we have an apotome, and we have a whole bunch of wide field scopes. So we can really try to set people up on the right scope. We try to do that. What's frustrating is to see groups that have only one confocal struggling to do everything on it. And I think one of the biggest misconceptions is that a spinning disk can be used for everything, and it can't really. Having said that, I don't have any more slides on this, but Olympus showed me a confocal just a few weeks ago that it has an Olympus stand, and then it has a new spinning disk confocal that Andor has put together, where you have this really high sensitivity EMCCD camera with just a 1/4 megapixel for those live cell fast imaging experiments. And they have a second camera for high resolution. It's a really good camera, 4 megapixel camera. And I thought, wow, this is a great idea. Like, why didn't people think of it sooner? But I was very disappointed with the images that came off of that 4 megapixel camera. Most of the field was completely dark because it's the Yokogawa spinning disk itself is not really designed for such a big sensor. So, but if they can sort that out, then it's a great idea to have a spinning disk with a high resolution camera and a high sensitivity camera in on one system. So that's a neat idea. Also, the new version of the Yokogawa has the pinholes further apart. So that should reduce the crosstalk between the pinholes for the thicker samples. So they've addressed 2 of my problems right there. And I think that's great, but there's going to be a trade-off. If you have the pinholes further apart, then you have fewer pinhole density, like fewer pinholes altogether. And that means you need longer exposure time, so you're not going as fast anymore, and you lose sensitivity, which was exactly what you were supposed to use the spinning disk for in the first place. So now they're kind of biasing it a little bit more towards, towards competing with the laser scanning confocals. But then are they going to become a jack of all trades, master of none? Like right now, they're kind of the master for certain live cell imaging applications. So I haven't tried it, so I don't know if that's going to pan out for them or not. And there was a third thing they did too. Oh yes, they have more than one. They actually have more than one pinhole disk now, more than one disk. So the reason that the spinning disk doesn't work for 10x or 20x is the size of the pinholes in that disk. And if you could choose a different disk for every objective, then there's no reason that you couldn't really do confocal with 10x or 20x. And this new system lets you put different disks in. Now we helped one of our users take care of an Olympus version of the spinning disk. It's a little bit different kind, and they have multiple disks, and they touted this as one of their big advantages. But in practice, in that case, nobody ever changed the disk because it was too complicated. But this new instrument is actually a motorized pinhole change, motorized way of changing the disk. So it sounds like there may be some improvements on the way for spinning disks that address some of these concerns specifically. But in the meantime, I would just watch out. Use the right instrument for the job. Would be my bottom line. Whoops. And that's it. Thank you. Can you speak nice and loud?
Sorry, this is for James and Judy, I guess, but since you're talking about new technologies, maybe you want to mention the resonant laser scanners that are coming up. Maybe I can get your comments on that and how you think they would compare.
Sure, yeah. That's a great question. So there are actually probably at least 3 other competing instruments that we could talk about.
Okay. One
is 2-photon. And for a long time, 2-photon, everyone wanted 2-photon, 2-photon, 2-photon. And I think now people are starting to realize, okay, 2-photon is really for very deep imaging. So if you can go 100, if it's 100 microns deep, you can go a little bit deeper with 2-photon, maybe 100, 150 or 200. Then another one is just doing wide field and then deconvolution, which is a mathematical way of removing the blur. There are some real strong proponents of that. But it generally requires a pretty rigorous acquisition, very rigorous sample preparation, and you have to measure point spread functions and physicsy kind of things like that, and spend a lot of time doing computing afterwards. So it's not as readily accessible to the average person. But then a third one is these resonant scanning confocals. The resonance scanner, there's a couple of new ones out right now. We tried one by Leica and one by Nikon recently. They're both very good. And the idea is, let's have a laser scanning confocal, but let's just drive the scanning mirrors really, really fast. So one mirror, instead of being a regular Galvo mirror that you can adjust the speed of it, it just oscillates at one particular frequency that's very, very fast. And you would think, wow, isn't that a great idea? Just good old laser scanning confocal, but way faster. And the only problem is that you usually don't have enough light. So already on the laser scanning confocals, I typically use them with about a 1 microsecond dwell time. Okay, so if you dwell for 1 microsecond on a pixel, then if you want a 1,000 by 1,000 pixel image or a 1 megapixel image, that's 1,000,000 pixels. So 1,000,000 pixels, a millionth of a second, that works out to about a second per image. That's pretty reasonable. The resonance scanner can go much faster, but in that 1 microsecond that I'm dwelling already, there's only a reasonable chance of having somewhere between 0 and 40 photons. You can do some calculations about the dyes and how much light you're collecting and how much the quantum efficiency of your detector. You're not likely to have more than about 40 photons. So if you go 2 or 3 times faster, that's all well and good, but there's no light left.
I'm guessing that
So,
the bleaching is not better either then as well.
so well, yeah. So the resonance scanners have been around for a long, long time, and they're only starting to make a comeback. And I think one reason they're making a comeback is that dyes nowadays are more stable. So these Alexa dyes, instead of fluorescein and rhodamine and things like that, when they were first developed, like resonance scanners have been around for a couple of decades, but nobody bought them for years and years. But now also the PMT detectors are a little more sensitive than they used to be. And when we demoed it, I was actually pleasantly surprised that they actually kind of work. Now, you don't get a reasonable image unless you start averaging. So you can scan like crazy, but then you have to immediately realize, oh, well, we can't scan that fast because it's too noisy. So you immediately start putting averaging in. And the question is only, by the time you put all the averaging in, like scan the same row 10 times, have you gained anything? And I found that I think maybe you can still gain a little bit, just because they've biased all the detector, like all the electronics and everything towards this fast scanning. So it does seem to speed things up by about a factor of 2 or something like that. And then there may be some advantage also to using a lower illumination power, so you're just dwelling for a really short time and then coming back and hitting it again by averaging the same row 10 times. There's a bit of an advantage in terms of reducing photobleaching. So they would argue that you reduce photobleaching by using a resonance scanner. I don't know. I think the jury is still out a little bit on the resonance scanners. What I really like about them, though, is that the resonance scanners usually come with regular scanners now, too. So you can use it like a good old laser scanning confocal, and then when you want the resonance scanning mode, you press a button, and a different set of mirrors move into place that scan like crazy. So when you need the speed, it's there, and then you just have to decide whether you're able to get a noise, keep the noise down low enough. That's a very good question. There's more than these 3 techniques out there. There's quite a few more.
So we are using images also so as image is data, but we want to be able to quantify them. So what will be the, I mean, this is a completely different topic, maybe another lecture about it, but when we try to do, let's say, like counting the nuclei, that is a different, like circular profile. Or looking at the branching structure like blood vessels, length, branching, or dendrites. Like, so, you know, I think that the shape of the profiles that you are studying is also very important, not only the thickness of the section. Because if it is something round, like a ball, kind of predictable, you want different type of resolution. Maybe the disk will be kind of fine for that to be able to do 3D reconstruction of the ball. But it's not good enough for a small, fine branching structures.
Yeah.
I think these are all things that I think needs to be thought about like the profiles. In that thing, that what I'm thinking is that, for example, for this epoch, like the GridBased, so the grids are horizontal. If I'm looking at a profile that it is like longitudinal, if I'm changing the orientation, do you think that the resolution will be different?
Yes. It does no optical sectioning like it doesn't do optical sectioning the same way in all directions. So if you have structures that are nice and linear, the apatome's a disaster for certain structures. And yeah, that's something that luckily you don't notice much in biology because there aren't too many things that are perfectly horizontal or vertical. So it's just lucky that most people would never notice it. Well, lucky, but also kind of unlucky, because by the time you've done the mathematical reconstruction, you've actually done something different in one direction than you have in the other. So absolutely, when you want to quantify things, you again need to pick the right microscope for the job. And I saw somebody, we were helping someone in the psychology building take care of their microscope for a bit, and they only had one confocal, and it was a spinning disk. And so they were using 10x and 20x in order to get a big enough field of view to image neurons. They wanted to like trace out these things. So they had thick tissues, because they wanted sort of the three-dimensional nature of it, low magnification, and then they were tracing out very, very fine structures. So they needed high resolution. So it's exactly the wrong microscope for 3 reasons, but then they would turn around and try to quantify it. And I said, good quantitation starts by taking good data in the first place. And it's totally the wrong microscope for the job. So yeah, quantitation, you're right, it's a whole topic unto itself. Yep.
One more comment for like everybody, but like when I took like statistics courses, like like it was like advanced statistics, the expert was saying basically that like you should talk with the statistician, before you start your study. I think that we are really lucky that our between hospitals and everything we have a group of experts like Judy and James and others. I mean, we should discuss with them before we start the study, rather than after try to fix it. Same thing with the statistics, or other techniques.
I can't agree more. Not only do a lot of people come to us after they've prepared their sample, but a lot of people come to us and they prepare a sample and they've already imaged it on whatever scope, and then they ask us to help quantify it. And the first step is usually, okay, we need to acquire this differently, or maybe even prepare the sample differently. It's definitely worth it to come and talk to your local facility people. It's probably true of more than just microscopy. And actually, we really, it's one of the things we probably like most about our job is working with people, right? We don't sit in some dark room on our own, and like we like getting involved with people's projects and providing advice and stuff like that. Don't you, Judy, or no? Maybe not.
Yeah, no, it's true. When people come and say their samples are ready, can I train them on the microscope? That's not my favorite request. Usually a new user just like to sit down and talk to them about the project, exactly for those reasons. Yeah. And we do have the software for deconvolution. It hasn't been used very much, but it's certainly worth trying. So we do have tools available.
So do you guys have a spinning disk? I think you have a laser scanning confocal.
We have a couple of laser scanning confocals. There will be a spinning disk coming. It's for Dr. Kapush, and the deal is that he will get a chance to kind of experiment with it and use it for several months, but eventually will become available for the researchers in general.
So are there a lot of people here doing live cell imaging? How many? A few?
We have a fully loaded wide field live cell system with stage-top incubators with the structured illumination, or whatever you want to call it, attachment. And some people think that, and we can deconvolve the data as well after you've acquired it.
Which is a whole other topic.
It's a whole other topic, and people disagree very vehemently about the best way to do that. Yeah, I have my own opinions, yeah.
Okay, well, thank you very much, everyone. Thanks for coming.